No, you guys are happy and quiet. And having breakfast. It's a good time.
Right now, for me, Matt, I'm just not sure what to ask. So maybe next week I'll have better questions. But right now, for me, I'm jumbled.
Yeah.
So
well,
I
it's
got
a
a lot of work to
lot
do.
of vocabulary to
I got a
get
lot of
down.
work to do.
Yeah. The nice thing is, you particularly, some of you guys, you're talking to other people, and that forces you to use the vocabulary to try to, make yourself understood and try to make other people understand or understand what other people are saying and make yourself understood. And that forcing yourself to use the vocabulary to discuss things is the best way to get it down as fast as possible. So you're doing the right thing there. So keep that up. Okay. So we talked, oh no, that's not gonna work. We talked yesterday about using mean and standard deviation together to talk about spread. So mean and standard deviation were a pair that gave us an idea of center and spread. But from our discussion on average, we know that mean has some disadvantages. It is affected by extreme data fairly dramatically, and there are times we don't want to use mean. So we had median. Median gave us a sense of center also, but instead of being based on value, it was based on position. We had to put stuff in order and all that. So that gives us also a sense of center, and it needs a buddy. It needs a friend, so we can have a sense of center and spread that's associated with position, just like we have a center and spread based on value. So I want to talk about that sense of spread today. And the nice thing is, we're probably at least somewhat familiar with it. You've probably dealt with throughout your life experiences, the idea of percentiles. So you might be told that, I don't know why a lot of my examples lately have been babies. My kid's 12. It's been 12 years. But anyway, you might be told your kid scores in the 90th percentile. For some sort of aptitude, or for baby, there's always like skull circumference, or whatever it happens to be. Scores in the 90th percentile for something. Well, what does that mean, scoring in the 90th percentile? Well, what that means is whatever value we're measuring here, be it skull circumference, be it aptitude tests, whatever it happens to be, the kids' scores are distributed however they're distributed, but your child here has scored in that 90th percentile, which means only 10% of like kids have a larger value, and 90% have a smaller value. Fair? So, you know, we often think of it as something, you know, being in the 90th percentile or the 95th percentile is good, but this doesn't have to be good. It could be the, you know, 90th percentile for, you know, aggression, because they're a very aggressive, you know, kind of mad child. It doesn't have to be something good or something bad, just some quality. So that would mean there are only 10% of children that are more aggressive than your child, which could be good or bad, depending on how you feel about having an aggressive child. And 90% have less. Fair? If somebody says we are in the, oh, let's say instead, we're in the, you know, 30th percentile. Okay, 30th percentile means essentially the same thing, that 30% are less than that, which would mean by implication 70% are above. So your percentile is always the proportion that are numerically lower than a particular score or value. So a nice example of a percentile that gets used a lot. So again, say we have some data. It's not necessarily normally distributed, but we have some data. And if we look at that 50th percentile, that 50th percentile breaks the data into two pieces. One section that has the lower 50%, and one section that has the upper 50%. We already have a name for this 50th percentile. What name do we have for that 50th percentile? What is that? What's that, Andrew?
Mean.
It's not the mean, actually. That's close. And I love the shirt, by the way.
The median?
But the median is that 50th percentile. Because remember, the mean, if we had like one huge score out here, the mean is going to be skewed towards that large value, right? But median, as you said, median is that middle center value such that half is below and half is above. So that 50th percentile is our median by definition. So when we talk about that median, we could have been saying the whole time, if we had wanted to, 50th percentile, and it would have meant the same thing. That seem reasonable? So the 50th percentile is already an important percentile to us. It again talks about center. But if we wanted to talk about spread, well, I'd want to talk about some other percentiles. If I knew some of the other percentiles, we'd have a sense of how spread out our data was. Well, what percentiles do you want to pick? You could pick any percentiles that you want to, technically, but let's pick some handy ones. How about the 75th percentile and the 25th percentile? That would break our data up into 4 nice chunks, right? Well, this is what we do. Now, we could have made other arbitrary choices. We could have looked at the 10th percentile and the 90th percentile instead. But breaking the data into nice fourths, into quarters, will tell us where the bottom 25% is, where the top 25% is, where the middle 50% is. It'll give us a lot of nice information that we can work with. So if we're going to break our data up into quarters, it might be nice to give those quarters a name. What do you want to call these quarters? I'm asking you that like you have a choice.
Quartiles.
Let's call them quartiles. Now, our quartiles are technically the boundaries of those sections. But the goal of quartiles is to do exactly this, is to take our data and break it into 1, 2, 3, 4 pieces. That's their job. So let's grab a set of data and do that real quick here. I'm going to put the data in order because we're going to be talking about position-based measures. So having the data in order is handy. So I'm just going to start that way. So let's say it's 3, 3, 4, 7, 11, 21. I took a big jump there. 1, 2, 3, 4, 5, 6, 23. Do I want 7? Yeah, I want 7. 24. Why not? So got it. N equals 7. 7 data points there. They're nice because they're in order, so finding some of our pieces will be easier. Wait, is that 7 or is that 9? 1, 2, 3, 4, 5, 6, 7, 8. That's 8. I don't want 8. How about 9? 9's better. Oh, I'll put a 1 down there. Don't get thrown off that I put a 1 down there. Okay, good. So if we wanted to find the 50th percentile, if we wanted to find that median, what's the median for this set of data? Well, don't be shy today.
0.5.
Could I get you to say that 7 with a lot more confidence?
9. But it's not really because the 3's ixnay each other out. So isn't it 11?
They don't.
Oh, okay. So it's 7.
So it's 7. Yeah, yeah. That the 3's don't combine. We need all that data in in order. So that 7 breaks us into 2 sets where half of the remaining data is above and half the remaining data is below. So that median is our 7, and that is our 50th percentile. Okay, so that breaks us into our top 50% and our bottom 50%. That's this 50th percentile here. Well, if we want the 25th percentile and the 75th percentile, we're essentially wanting to break these remaining 2 in half. So essentially what we're going to do is find the median of these 2 sections. So for this first set of 4, what's its median?
3.
3. So that 3 is our 25th percentile, and what we're going to call our first quartile, Q1. That is our 25th percentile. But we call it our first quartile. It's our first cut for our quarters. What about the latter set of data, the 11, 21, 23, 24. What's its median?
21.
Yeah,
It's 23.
no.
Or is it in the middle?
22.
It's 22.
It's in the middle of those. Remember, if it's an even numbered set, we had to take the mean of those two. So 21 plus 23 divided by 2 is 22. Fair?
Okay.
So that 22 is our 75th percentile, is our third quartile. Wait, I went from the first quartile to the third quartile. Where's the second quartile? He asks.
It's the middle.
Yeah, it's that middle one. It's that 7. So that 7 is our second quartile. And those 3 values break our data into 4 pieces. So our Q1, our first quartile, are 3. Our second quartile are 7. Our third quartile are 22. Tells us where those breaks are. So that's our 25th percentile, our 50th percentile, also our median, and our 75th percentile. Now, sometimes it bothers people that, well, I've got 3 quartiles. Quartiles is fourths. I kind of want 4 things when I talk about quartiles, right? We could try to fix that by saying, okay, I've got a 4th quartile at the end of my data. I could say, okay, I got a 4th quartile at the end, 24, at essentially our maximum. You notice that maximum is in quotes. That'll be an issue later. But if I'm going to put the maximum in, I kind of want to put the minimum in too, right? So that minimum is often referred to as our 0th quartile, or start. So our 0 quartile, where we begin, our first cut at the first quartile, 25%. Our second cut, our second quartile at the 50%, our third quartile at the 75%, and the 4th quartile at the maximum. These values together give what's called the 5-number, because there are 5 numbers, 5-number summary of our data. Does that seem reasonable so far? Okay, so if we're going to practice this, I kind of want a chunk of data. So I'm going to grab a chunk of data here. Here's a chunk of data. So given this data, produce a 5-number summary. I'm going to give you a little while to do that. There are some issues that may come up. And if they come up, we'll talk about them. But I kind of just want to see if you were thrown into that, what would you do with it? So let's see, I'll give you 4 minutes. Produce 5-number summary for that data. I'll be right back. Oh, and Jesse, we could call it the 100th percentile if we wanted to. We just don't tend to. There are a couple reasons we'll talk about in a bit why we probably don't tend to. But I'll mention that of the time. But it wouldn't be unreasonable to call it the 100th percentile. We just don't. Who's the meanie that gave us data out of order? Come on. Oh, I forgot the 13. $18. Well, that's not right. Oh, I forgot the 14 too. Yeah. We're talking about making sure you type in all your numbers, right? Got to make sure you can write all your numbers down. So that's 19, and the array's got 20 minus 1, so 19. Okay. So got all the numbers down in there. That's good. That's helpful. Then we got to find our median. There's a nice trick for median that we haven't talked about yet that comes in handy when you have longer and longer sets of numbers. We have 19 values here. So if we want to know what position our median is going to be in, there's a nice little tool. Take your number of values, add 1, and divide it by 2. In this case, that's going to be 19 plus 1 divided by 2 is going to be 20 divided by 2 is 10. That means the 10th value is going to be our median. It's a nice tool, particularly when the number sets get to be like 158 and you're wondering where your data point is. So that's a nice tool to keep in mind. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That second 8 is going to be our median. So that's our Q2. Fair? If you ever want to kind of check and make sure, remember that that should break our set into 2 equal pieces. So 1, 2, 3, 4, 5, 6, 7, 8, 9 below. 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, that's below, sorry, below and above. So those 2 lists should be exactly the same length. Now, if we would have had an even number of data points, we would have had what's, the kind of in-between value, right? So for example, if, it's a big if, but if our n was equal to 20, we'd have had still n plus 1 divided by 2 would have been 21 divided by 2, which would have been 10 and a half. So we'd have gone to the 10 and a half location, and that would have made us take the mean of the 8 and 9. So we got an 8 and a half, and it would have broken us up into a lower set with no exclusion and an upper set with no exclusion. Both of those would have contained 10 data points. When we have a solid Q2, when we have a solid value there, notice we exclude that. There we go. We kind of exclude that 8 from both the upper and lower, so we can make them the same size. Then we do the same thing. We grab the lower set, find its median. That's going to be our first quartile. The upper set, grab its median. That's going to be our third quartile. Has 9 values. 9 plus 1, 10 divided by 2 is 5. So 1, 2, 3, 4, 5. That 5th value is going to be our Q1. Cool. Similarly over here, 1, 2, 3, 4, 5. The one in the middle going to be our Q3. Our sort of maximum value, I keep saying sort of and putting it in quotes. Talk about the why in a minute. But our max value is at 19. Our minimum value is that 0. So that becomes our 5 number summary. Our Q0 or a minimum. In most of what I think this particular textbook and the computer does is it will call this minimum, Q1, Q3, and maximum. But you'll see a lot of applications call them Q0 and Q4 as well. So I want you to be familiar with that. I'll often call them that just because I like it. But that's our five number summary. I am going to keep putting these in quotes, min and max, because I want you to be anxious about that and wonder why I keep doing that. Because when we explain why, I want you to remember. So I want to keep you wondering about that. So questions where any of those came from? Camilla, it looks like you were off a bit in your count. That's easy to have happen, particularly when there's lots of numbers like this.
I know the process, but you know, I do that often.
Yeah.
I put the wrong number or I forget a number, and I think I forgot a number, and that's why mine.
Yeah. I forgot several when I first did it.
Actually, yeah. Yeah, I forgot 13.
So all of us good? Okay. So this gives us a nice sense of how our data is arranged. But it doesn't really answer quite yet this question of, I wanted a value here that's going to take the spot of standard deviation and give us a sense of spread in a single value. This 5-number summary, gives us a sense of spread fairly nicely, but it's not a single value for it. I kind of want that single value. That single value, there are essentially 2 choices. There's the meh choice and the good choice. I'm going to tell you what the meh choice is, and we'll almost never use it. The meh choice is range. Range is quite simple. Range is the maximum value minus the minimum value. So in this case, the range would be 19 minus 0. The range would be 19. It just tells you how much or how wide your range of data is. This data is spread out over 19 units. Which, okay, good, nice to know. But the trouble with range, if we had one data point here that was an extreme value, like say this was 39 instead of 19, that's going to make our range look huge, right? Part of the point of using measures based on position is that I don't want to be affected by extreme values. I want to be resistant to the effect of extreme values. We even call them resistant measures. So range isn't a resistant measure. Range is highly affected by extreme values. So I kind of don't like range. I'm not a big fan. There are uses for it. You'll be asked for it. It's easy to find, which is nice, but it has some huge disadvantages that don't associate well with median. The better one, the one that we will use, is, I don't want to quote that, is interquartile range. So it's similar to range in that it does give us a range. But instead of being the range between these outer quartiles, the min and max, it's the range, the distance between the inner quartiles. the range between Q3 and Q1. So that third quartile minus that first quartile for our interquartile range, IQR. One of the biggest advantages of interquartile range is it's fun to say. You know, what did you do today? Oh, I calculated interquartile range for a data set. Oh, don't you sound cool? The other advantage is it's not resistant to extreme values. If we look at, if we did change that 19 to a 39, the interquartiles don't care. If we had a value down here, negative 84, okay, fine. The interquartiles don't care. So it's not affected by those extremes. Essentially, instead of looking at how wide is the range of all of our data, it's asking how wide is the range of our middle 50% of data. That makes it more similar to that standard deviation, where it's okay, standard deviation was essentially where's that middle 70% of your data. Interquartile range is where's the middle 50% of your data. But they'll both giving a nice sense of where is that kind of typical, where's that middle spread. Fair? So in this case, our interquartile range would be the 13 minus 4. So our IQR, our interquartile range, would be what? 9. So when we talk about, going back up here, matching up mean with standard deviation to give us a value-based center and spread, our median is matched up with interquartile range to give us a sense of center and spread based on position. So when we use mean, we'll usually connect it to standard deviation. And when we use median, we'll usually connect it to an interquartile range. That seem reasonable? So when we're given a nice set of data, we'll often want this 5-number summary, particularly if it's got some extreme values and we want to be talking about position instead of value. And that interquartile range kind of takes a similar place as standard deviation does. And you can see right away, it's a lot easier to calculate than standard deviation. Remember all the work we had to do for standard deviation? All the little subtractions, all the squares, taking the adjusted average, taking the square root. Standard deviation is a lot of work because we care about the actual values. Interquartile range, as soon as our data is in order, it's not that bad to find. Fair? Now, in some ways, it's not as informative as standard deviation. Remember, standard deviation, we had a lot of information about percentages in those different sections, where almost all of our data was, all that kind of stuff. We don't quite have that much information with interquartile range, but we do have some things like that almost all idea with interquartile range. What order do I want to do this in? Yeah, let's do it in that order. So let's talk about what I mean by that. So let's say we have some data, and that data is all spread out. I'm going to use a dot plot because we don't use dot plots enough. So let's say we have a bunch of data here. If we found our mean and standard deviation, I'm going to do mean and standard deviation in blue. Our mean, well, this large value out here is going to pull our mean a little bit. It's going to skew it a little out there towards that large value. So say our mean's about there, and our standard deviation should be such that most of the data, 70% of it, the typical data, lands within one standard deviation. 95% of our data should be within 2 standard deviations. So we might have a value that's outside of that, but almost all of our data should be within 3 standard deviations, right? So essentially, our data set should be roughly 6 standard deviations long. Does that seem reasonable? Anything outside of that, if there happened to be like a single really low data point out here somewhere, we might consider that data point to be freaky. I don't want to say unusual, because unusual would be anything outside 2, right? This data point's already unusual. We might call anything outside that 6 standard deviation interval, we might call it an outlier. You've probably heard that term every once in a while, an outlier. It's a data point that is outside of where our data should be, where our data ought to be, where, you know, everything is supposed to be. So in our mean standard deviation way of looking at the world, we have a way to consider whether or not something is an outlier. That is it more than 3 standard deviations from our mean? If it is, we say that point is an outlier. Now, what we do with the fact that it's an outlier depends on what we're studying and how we feel about outlying data. But our technical term for is this an outlier, this is one of the ways we'll define something as an outlier. Is it more than 3 standard deviations from our mean? Well, that's a standard deviation mean argument. We also want to have a sense of outlier based on position. So we want to have a way of defining whether or not something's an outlier that, instead of being mean and standard deviation, is based on median and interquartile range. So we're going to do essentially the same thing. We're going to say, okay, where is our mean? Our median. Our median should be a little more towards the center than the mean was, because this extreme value isn't going to pull it off. And our 3rd quartile and our 2nd quartile, if we were being really cautious here, we'd be counting up how many dots are in each of those sections, right? I'm not going to be that careful, but. And we have what looks like a minimum down here, but I do keep putting that in quotes. Is it driving you nuts? You're curious why it's in quotes? Good, that's what I want. And we have our maximum, quote, maximum out here. But is either that minimum or that maximum an outlier? Well, our standard deviation rule gave us a way to talk about outlier, but that's actually not the super formal. This book uses that as a rule for outliers. But the technical rule for outliers is actually an interquartile range argument. So what we could ask is, well, this is our interquartile range. We could ask, we're not going to, but we could ask, if we go out our interquartile range, if we go that distance or that many values outside of Q3, is there anything outside of that? But unfortunately, that interquartile range, it doesn't tend to be that wide. So if we used, are you an interquartile range value outside of Q3 to define outliers, we'd have a lot of things that were outliers that we don't want. So we want this not to be the interquartile range. We want it to be bigger than that. How much bigger? Well, the convention in statistics is 1.5 times bigger. So let's say, for sake of argument, our median was 10. Our Q1 was 4. Our Q3 was, I don't know, say 13. Oh, 13? Yeah, sure, 13. And then our IQR would have been 9, the difference between 4 and 13. To see if something is an outlier, how far out from that 13 would we go before we try to say something's an outlier or not? Well, we'd take the Q3 and we would add not our interquartile range, but 1.5 times our interquartile range to it. So 13 plus 1.5 times our interquartile range. So 13 plus, what's 1.5 times 9? 13.5. Yep, 13.5. So that would give us 26.5. So that 26.5 would be the limit for values that we would consider non-outliers. Anything outside of that would be an outlier. Anything inside of that is a non-outlier. So let's say this big value we have here is at, oh, I don't know, say it's at 23. Is that 23 an outlier? No. So, okay, that's our max. What happens if we go the other way from our Q1? So we would take our Q1, instead of adding, we're trying to go lower, so we'd be subtracting. So subtract 1.5 times our interquartile range. So that's going to be our 4 minus 1.5 times 9. So 4 minus 13.5, which is negative 9.5. Can we have negative values?
Probably depends on the type of data that we have.
It does. If our data allows for negative values, we can totally have negative values. It was really funny watching you guys. All you guys are kind of like, you know, moving around a little bit. And I asked, can we have negative values? And all of you stop. It was hilarious. But yeah, if like we're talking about, say, temperature, we're talking about, you know, how much money we have, we can have debt versus capital. We can, you know, yeah, negative values are fine. So let's say that negative 9.5 lands there. And this value here was bigger than that. or more negative than that. Let's say that value there was at negative 11. That negative 11 is more than 1.5 interquartile ranges from an inner quartile. So that negative 11 is an outlier. Fair? So if we're going to list our min, first quartile, second quartile, third quartile, and our maximum, for this data set, as I have it labeled here so far, what's our maximum value? Let's start at the bottom here.
23.
The 23. What's our third quartile?
13.
Our second quartile?
10.
That's our median. Our first quartile?
4.
But what's our minimum?
Not the 11.
Good. Not the negative 11. You're like, it's a trap. I can feel it. The minimum and maximum of our data set, the reason they're in quotes, that minimum and maximum have to be the minimum and maximum non-outlier. So that negative 11 isn't what we're going to call our data set's minimum. Neither is it the negative 9.5, by the way. That negative 9.5 isn't a data point. We have to go all the way to the smallest or the nearest non-outlier, the least non-outlier, which, you know, in this case, based on the scale here, might be negative 1. Okay, so that minimum is negative 1. You might say, yeah, but we have a value that's smaller than that negative 1. Yeah, but that value is freaky, right? If we told people that our minimum was 11, if that's what we advertised, then we would be giving people the impression that there were values in between negative 11 and 4, that that was a populated interval. Is that happening here? No, there's a huge gap there. And we want to make sure people are, you know, aren't thinking there's data in there. Fair? So our minimum non-outlier is that negative 1. From the negative, whoops, that was the eraser. From that negative 1 to 4, okay, that's a populated set of data. Fair? So, okay, why have I been putting those minimums and maximums in quotes? Because they are the minimum and maximum, but they're the minimum and maximum non-outlier. So if we go back up here, I'm gonna clean some of this up just because it's a mess. If we go back up here, for this data set here, where we said our minimum was 0 and our maximum was 19, well, that's only true if that 0 and 19 aren't outliers. Fair? How do we test to see if they're outliers?
Go 1.5 times the interquartile range outside the third quartile, the first one.
Yep. Take our IQR. IQ 9. That meant. Our IQR. Multiply it by 1.5 and add or subtract it from our outer quartiles, Q1 and Q3. 3. So for our upper, keep doing that today. Our upper limit is going to be that Q3 plus 1.5 interquartile range. So what was our Q3? 13 plus 1.5 times our interquartile range was 9. Boy, those numbers look familiar. Did I really do that? I did. Silly me. But anyway, that was what, 13.5. So 26.5. So okay, that maximum, that 19 is well within our 1.5 interquartile range, plus our outer, or our Q3. So it's a fine max. It's not an outlier. Similarly, our lower limit our Q1 minus 1.5 IQR. Again, 1.5 times 9. It's this time we're subtracting it from 4 again. I did pick the same numbers. Oh well. 13.5, which is negative 9.5. And that 0 is well within that range as well. This data didn't have any kind of crazy outer points. So that min and that max are fine. That seem reasonable? Now, your book and the computer does something I don't like, and I'll show you. It gives us a nice question like this and says, okay, find the interquartile range. We can do that. Find the standard deviation, particularly for this data set. Use your calculator or Excel. And we'll talk more about that on Monday. We'll probably do that lab on Monday just because we lost a day this week. So we'll push that a little bit. And apply the 1.5 interquartile range to search for outliers. Report the lower and upper cutoffs. Okay, so those would be our lower limit and upper limit like we found here. And are there any outliers? You can say yes or no. Great. I have no problem with any of that. It then goes down here and says, apply the 2 standard deviation rule to search for outliers. There is no 2 standard deviation rule for outliers. There really is no 3 standard deviation rule for outliers. Outliers are technically defined as being 1.5 interquartile ranges outside of Q1 or Q3. That's what it means to be an outlier. This textbook is being a little bit loose with its definition of outliers, and I don't like it because I'm grumpy. What's the technical term we use for being outside of 2 standard deviations? What was the vocabulary word we keep using?
Unusual.
Good, Andrew, unusual. So this should say, apply the 2 standard deviation rule to search for unusual values. And you want to say report the lower and upper cutoffs for unusual values? Great. Add and subtract 2 standard deviations from your mean, to find that upper and lower limit. Great. Are there any unusual values? Yes or no? Great. It bugs me that this book extends its definition of outliers, but it does. So I can do nothing but gripe about it. For the most part, it's actually a very nice textbook, but this one detail gets under my skin a little bit. The nice thing is, on your tests, I can go in and change that language and call them unusual. And I do. So be careful about that. For our discussions, if it says outlier, 1.5 interquartile range from the inner quartiles. Standard deviation, it's a different argument, so it's our typical, unusual, almost all. Fair? The nice thing is, the homework in the textbook never says, is this an outlier or not? It always says, apply the 1.5 rule or the standard deviation rule. So it's never ambiguous about which one it wants you to use. It just overextends that definition, in my not so humble opinion. So just be careful about that. You know, and I want to mention that because I will be not consistently in line with how your textbook wants to say it. So it's good for me to note that, because if not, it could throw you guys off more. But of course, I'm right. So what are you going to do? What are you going to do? Always assume your professor's right, right? At least when you get to the tests anyway. Then you can think whatever you want after that. So do be careful about that. So this interquartile range tool does take a little bit to get used to. It does take some playing with. So we're going to get you some chance to practice that in the homework. Before I let you go today, though, there is one more tool I want to introduce you to, so you can play with it between now and Monday. And that is the idea of a box plot. This 5-number summary is really handy. So I'm gonna grab this data here. This 5-number summary here is a very nice summary of data. It's a very nice way to kind of break down where our data is, but it is essentially still just a pile of numbers. And people are really very visually oriented. We're a primate. Primates had to make sure when they jumped around in trees, they didn't slam into things. That's why we have stereoscopic vision. That's why we have the giant occipital lobe in the back of our head. We are visual creatures. We have one of the best eyes in the natural world outside of birds of prey. So let's take advantage of that and find a nice graphical tool that will list these 5 numbers in a way that's nice and visually impactful. Just to take advantage of biology, right? And a box plot does that. It plots these 5 values in a visually impactful and commonly used way. To make a box plot, we need a scale. So I'm going to make that scale go 0, 10, 20, negative 10, negative 20. We're not going to need the negative all the way down to that negative 20, but that's okay. And just for the clarification, I'm going to put in those 5s. So we need a scale. Notice this is a 1-dimensional scale, not a 2-dimensional scale. It's a horizontal axis, not a vertical axis, and a horizontal axis. Not both, just one axis. Fair? You can actually do box plots vertically if you want to, but it's one axis, not 2. And on this axis, or technically above this axis, I'm going to plot these values. Our minimum was at -1, so we have a minimum here at -1. Our first quartile was at 4. Our second quartile, or our median, was at 10. Our Q3 was at 13, so that's a little bit tighter, that's nice. And our maximum was way out here at 23. Well, okay, so we've traded a bunch of numbers for a bunch of lines, but it's called a box plot, right? Where's my box? The box goes in those inner quartiles. So the box goes from our Q1 through our Q2 to our Q3. So that box represents the middle 50% of our data is inside that box. Notice we can see that the median is pushed a little bit towards the upper value. So that box is actually broken into two boxes. And because there are quartiles, we know that 25% of our data is in that box, 25% of our data is in this box. Outside of that box, our upper 25% is in that line. That line is technically referred to as a whisker. I know, I didn't make this stuff up. Often referred to as a box and whisker plot, if you want to get technical. And then that whisker. So again, 25% of our data is in that whisker, and 25% of our data is in that whisker. So it nicely visually displays that we have a lot of data in this upper whisker, so this data is fairly spread out. This data between Q2 and Q3, that was fairly tightly clustered. These are a little bit more spread out. And that gives us a sense of where our data is and how it is spread out. Fair? So it's a visual representation of that 5-number summary. But wait, you should be saying, what about this outlier at -11? Do we want to represent that outlier at -11 somehow? Yes, we do. And we do that by putting a dot at that -11. Now, this goes back again a little bit to what, Andrew, what you were talking about when you said the minimum's not that 11, right? Imagine if instead we drew the whisker all the way out to that 11. Again, that would imply to somebody looking at this that we had data spread out between those two. And we don't have data spread out between those two. We have data between the -1 and the 4, and then we have this lone point out here in the middle of nowhere. Fair? So that's another one of those reasons why we don't want to consider that -11 to be our minimum. We want it to be labeled as it's something outside of our normal set. Fair? If we did have more data populated in there, well, that would move where our first and third quartile were. They would lengthen our interquartile range and could bring that -11 into our values. But that's not what happened. We had this big blank gap, and we want our data to reflect that gap, and we want our box plot to reflect that gap. Cool? Have any of you guys seen box plots before out there in your travels? Some of you are like, I think I might have. You probably have. They're actually really common, and you'll probably see them more and more as you go along. Particularly if you're going into almost any field that requires, this course as a prerequisite for it, you'll start seeing box plots more and more. And it's also one of those things that as soon as you learn about box plots, suddenly you'll see all these box plots around you. Just because that's how life works. So they are actually really, really common tools, especially for comparing data sets. Okay, so anything else I want to make sure? We got box plots. I want to make sure I'm happy with our 3-4, 3-5 stuff. I think we're good. I think that puts us as caught up. Yes and yes. So the last exam is going to be cumulative. That actually ends up being a really good thing because by then you're so used to all this vocabulary that you're like, wait, you're just asking me to make a box plot? We've been making box plots for weeks. Well, yeah, but we didn't know that when we came in. So that's a final thing. So that's always nice when that happens. And I would certainly wait until Monday, because then on Monday you guys can ask anything you want. So yeah, I would leave the test alone until then. Cool. Because then we can ask questions and we can get everything cleared away. See, Jesse, Camille, you guys talked about having a study session tomorrow at 10:30. I should be around, so send me a message if there's anything that you guys need.
Okay.
But before I let you go today, anything I can do for anybody before you trundle off?
Well, I have just two questions.
Shoot.
I thought about, well, what about the 26.5? It doesn't get any mention.
No.
It's outside of the maximum.
Yeah, well, remember that 26.5 isn't an actual data value. That 26.5 is a boundary that we calculated, but not a data value. So you're right. That negative 9.5 and that 26.5, they don't get any love at all. But that's because they're not actual data points. And it is common for people to make that mistake. So I'm glad you asked. They'll try to have that on the summary, or they'll try to have that on the box plot somewhere. It doesn't represent actual data, so it shouldn't occur there.
And the other quick question is, how would this apply to my real life? I mean, right now, to me, it's just a bunch of numbers.
Well, the nice thing is we will play more with, okay, trying to use this to make decisions as we go along. But one of since we're talking about spread, if you're looking at, say, different investments or different tools, I was buying drill presses the other day, and I was looking at the range of speeds that I can get from the different gearings. And one of them, the data spread was much tighter than the other. Well, that tight data spread gives me consistency, but less flexibility. So being able to compare the different ranges of data and different spread of data can inform what I'm trying to do based on what my priorities are. If my priorities are even consistency, I might want a tight spread, versus flexibility, I might want a wider spread. So, you know, go ahead.
I was just going to say, I can relate to the variable speed drill press because I'm more familiar with a variable speed drill press than I am just numbers. But I understand. I'm having a challenge here because I'm having to rechange some of my thinking and vocabulary, and it's a little difficult right now, but I'll get there, I'm sure.
Well, you guys can see what I was saying those first couple of days about we're not doing a tremendous amount of algebra, a tremendous amount of math mechanics. Yeah, we did a little bit of solving when we had to find that first thing today. You know, there was a little bit of solving in here, but that's not, you know, big algebra. And we're not going to do any real big algebra. What this class is putting all of these little weird mathy things in perspective, getting that vocabulary down, getting all that meaning down. So it is a very different set of challenges than most of your math classes tend to be. So you're right, it's a very big reorientation about vocabulary and meaning and perspective. So it should take a while to get used to that. The nice thing is the more we use it, the more we use it to accomplish things as we go along, the more perspective we'll get on it.
Okay.
So that does strengthen, but you have to do what you're doing, which is talking to people, putting that time in. It will come together, but it's not. People often think, well, oh, stats, it'll be easy because there's not much math. Well, there's not much calculation, but there's a lot of math and a lot of vocabulary and a lot of knowledge and perspective to get down. And you're not the only one who feels that way, trust me.
Well,
I mean, right, guys? Everybody else is like, no, yeah, we're fighting with those same things.
well, good to know that. Thank you, because I was a little, I don't know, I've made some mistakes and it just, anyway, but thank you.
You're just the brave one who will talk about it.
Well, okay.
Okay. Oh, we're afternoon. That's okay. Anything else you guys need? Again, send me messages if something comes up. And I'll talk to you guys as we go along. And worst case scenario, I'll see you Monday.
Thank you.
Hey, Jesse,
Yes.
you don't have to wait till Friday to like see if someone's mathing, because I math Monday through Thursday and Friday. I mean, I'm always doing math until my homework's done. So if you're
Wow.
stuck or something, just text me and be like, hey, you're mathing. We can jump on the Zoom and we could do it together, because I'm probably